Hello students, let us continue our discussion on the thermodynamics of open systems, where I have introduced you to the concept of chemical potential, and we have seen that depending on the situation that we have in our experiment, in that case system can exchange matter with the reservoir, whereby I can define the equilibrium state of the system by introducing a new intensive variable, which is mu, as shown here. And I've also introduced you to the commonly used definition of chemical potential as a partial derivative of the Gibbs free energy with respect to the number of particles of the ith type present in an M component system. And here we find that dg is given in terms of dt, dp and dni, and by definition Gibbs free energy is an extensive property and mu is an intensive property. Now we have started talking about what happens to chemical potential for a pure substance where the number of components M is equal to 1. So in this case, we have already shown that mu is nothing but the molar Gibbs free energy at the given temperature and pressure at which I have taken this partial derivative del G del N. Therefore, using the dependence of Gibbs free energy for one mole of a substance on temperature and pressure, I can very easily write down d mu is equal to minus dm into minus sm into dt plus vm into dp. So what are these quantities? Sm is the molar entropy, and what is Vm? Vm is the molar volume. Now, what is the significance of this relationship? Please remember, temperature and volume, these are intensive quantities. And here I have Sm and Vm multiplying them. But these are quantities which are independent of the number of moles which are present in the system. Therefore, on the whole, this expression expresses the variation in the intensive quantity mu as a function of temperature and pressure. Let us next think about whether we can determine the chemical potential for an ideal gas, where I do know how to express Vm, that is the molar volume, in terms of the temperature and the pressure of the gas. If I take this expression and put it in the equation that I've already derived, what do I get? I'm going to get d mu is equal to minus Sm into dt plus, now instead of Vm, I'm going to put in this expression, and therefore the second term now will turn out to be RT by P into dP. If that is so, then for an isothermal change in state, let us say that the ideal gas is undergoing an isothermal change in state from a pressure P0 to a pressure P. And here I'm using the notation that P0 is the standard pressure. And then I can write down that this equation can now be integrated from starting from the standard state where mu is equal to mu naught, and I go over to the pressure P where mu is equal to some given value mu. And under such condition, as you see, that it's isothermal and therefore dt would be equal to 0. So how many terms shall I have on the right hand side here? On the right hand side, I'll have only one term remaining where temperature will now be outside the integration. And the result of this integration would be mu Tp, that is equal to mu naught T at the standard pressure plus RT ln P by P naught. So very easily, as you can see here, we have been able to estimate the value of chemical potential as a function of temperature if I know the value of chemical potential at standard pressure. So P naught is known to you. This should be some constant at a given temperature T. Therefore, knowing P, I know how to estimate this portion. So let us move ahead and think about for a mixture of M components where I know the definition of mu I. If I have an initial equilibrium state when the system is present at a temperature T, pressure P, and N1, N2, etc. are the number of moles of the component of type 1, 2, and so on. I'm going to look at a final equilibrium state where in general I have carried out the following changes. At the final equilibrium state, the temperature has changed from T to T plus dt. The pressure has changed from P to P plus dP, and each of the components now have undergone an infinitesimal change so that for the ith component, I have the number of moles of the ith component changing to Ni plus dNi. Now, for this entire change, I understand that by definition, dG would be minus SdT plus VdP plus mu I dNi. Now, if I have an isothermal and isobaric process, in that case, what would be the change in state that I am looking at? So I will be maintaining the same value of temperature and pressure in the final as well as in the initial equilibrium state. But now N1 will change to N1 plus dN1. So Ni in general will be changing to Ni plus dNi. And since G is a function of all these variables, now I can use this expression and write down that dGTP, that is the infinitesimal change in the Gibbs free energy under such isothermal and isobaric process, will now be equal to summation over I mu I dNi. So with this, we understand that a fluctuation in the composition of the system does lead to an infinitesimal. If the fluctuation is infinitesimal, in that case there will be an associated infinitesimal variation in the Gibbs free energy even if I'm maintaining the system at constant temperature and constant pressure. Now with this, let us extend our consideration to find out the chemical potential in a mixture of capital M ideal gases. So here I would assume the following. I would assume that the mixture that I am talking about here, this behaves ideally at a temperature T and pressure P. And I'm going to use certain quantities which are very commonly used in the description of such mixture. The first quantity that I define with respect to the ith component is the mole fraction. So this mole fraction is given this symbol xi, and the mole fraction xi is defined as here Ni divided by n. So what is n? N must be the summation of over all the number of particles present in the system. Now I introduce another quantity, which is the partial pressure. Now here, by Dalton's law, I would say the partial pressure Pi corresponding to the ith component of this ideal gas mixture is proportional to the total pressure P at which the system has been maintained, the mixture has been maintained, and the other quantity that appears in this equation is the mole fraction Xi. With this, our idea is, in this mixture, can I find out the chemical potential of the ith component? So let us see how we can go about performing this task. I'm going to start by using the expression that I have derived for an ideal gas in my earlier slide. So what is the chemical potential of the ideal gas I when it is present at a temperature T and its partial pressure in the mixture is Pi? Now, using the result that we have obtained before, I can write down mu I will then be equal to mu I naught plus RT ln Pi by P naught. In this case, I'm going to use the definition that the partial pressure is equal to Xi into P, because my system is maintained at a temperature T and a total pressure P. If that is so, I can rewrite mu I as now mu I naught as before plus RT ln P by P naught, but now I have taken out the dependence on the mole fraction of the ith component from the logarithmic term. Now I will go ahead and look closely once again to the two terms that I have highlighted here in blue. Now what is this equal to? This must be equal to mu I star Tp, that is mu I naught plus RT ln P by P naught. Have we seen this expression before? The answer is yes. If the ith component was present only as a pure phase, I mean if I only had the pure ith component at a temperature and pressure P, in that case the chemical potential of this gas at that temperature and pressure would be given by this. And therefore, I am adding one star as superscript here to mention that the sum of these two terms actually corresponds to the chemical potential of the ith component in its pure phase. And that tells me that now I can write down chemical potential of the ith component in a mixture of ideal gases maintained at a constant temperature T and the same pressure P, total pressure P, that must be equal to the chemical potential of the ith component under identical conditions of temperature and pressure when it was present in its pure state, plus another term that depends on the mole fraction of the ith component in the mixture. And what is going to be my immediate conclusion from here? Here I understand that in a mixture, Xi is always going to be less than 1. As a result, I will have this term must be less than this term. Clear? Therefore, I would say that the chemical potential of the ith component in the mixture is always less than chemical potential of the ith component in the pure phase. That is because when I have Xi less than 1, RT ln Xi is going to be a negative quantity. Therefore, you will take away this part from the pure phase value of mu I to give you the value of mu I in the mixture. Now, if I go ahead and now try to understand how to associate this concept of chemical potential to the transfer of matter, this is what we are going to do. Now, once again, I'm going to take this composite setup where I have a compartment A and a compartment B which can exchange matter between them. Now, at a constant temperature and pressure P, I'm going to say that these two compartments have a common component I, and dni moles of component I is transferred from A to B. Then I understand that there will be a change in the Gibbs free energy of the system in both the compartments A and B. So what is going to be the change in the Gibbs free energy in compartment A? This is going to be at this given temperature and pressure, dGA is going to be mu IA into minus dni because it has lost dni moles of the ith component. So what is mu IA? That is the chemical potential of this ith component in the compartment A. Since the compartment B has gained dni moles of the ith component, what is going to be the corresponding change in the Gibbs free energy? That is given by dGB, and this is going to be mu IB into plus dni. Now, mu IB corresponds to the chemical potential of the ith component in the compartment B. So due to this transfer of matter from A to B, what is the net change in Gibbs free energy at the given constant temperature and pressure? I can evaluate that provided I can sum up dGA and dGB. And by combining these two expressions, now I can say that dG is equal to mu IB minus mu IA into dni. So now you see that we are looking at a process which is resulting in a net change in the Gibbs free energy at a given temperature and pressure. Now, what is the condition for a spontaneous transfer of matter in a situation like this? In this situation, if I have to have a spontaneous transfer of matter, the net change in Gibbs free energy dGTP must be less than 0 in the direction of transfer. And therefore, I can say if there is a case where mu IA is greater than mu IB, what would happen to dG? If mu IA, so we are going to consider this particular expression and say that if mu IA is greater than mu IB, then the term within the first bracket, that is going to be negative, and consequently, since dni is a small but positive quantity, therefore dg is going to be less than 0. Therefore, if the chemical potential of the ith substance is higher in the compartment A in comparison to the compartment B, I can very easily conclude that a spontaneous transfer of matter will take place from the region A to the region B. Now let me consider the next case where mu IA is less than mu IB. So in that case, this term in the first bracket, that is positive. Since dni is anyway a positive number, small but positive number, therefore in that case dg Tp is going to be greater than 0. So I would say that here, if it so happens that the chemical potential of the ith substance is higher in B, then a spontaneous transfer of matter from A to B is not possible. Now comes the third case. The third case is where mu of the ith component in compartment 1 is equal to the corresponding value in the compartment B. And what does it tell me about dgTp? It tells me that under that condition, dgTp is going to be equal to 0. So if I use these three relationships and now look at the condition of spontaneous transfer of matter, then I understand that spontaneous transfer of matter occurs from a region of high to low value of mu under the given condition of temperature and pressure. Therefore, at equilibrium with respect to matter flow, the chemical potential mu of the ith substance in the given case must be having the same value everywhere throughout the system, irrespective of whether I'm looking at some region in A or some region in B. And therefore, it says that the way we have defined the chemical potential, it takes care of the fact that just as I could use temperature to indicate the condition of thermal equilibrium, pressure to indicate the condition of mechanical equilibrium, I can have the chemical potential indicating to me the condition of equilibrium with respect to transfer of matter. Okay, so what we have learned from here is once again that we have been able to identify an intensive variable with respect to transfer of matter, and till now we know that this intensive variable can be determined in terms of the ideal gas, whereby I can identify chemical potential as a function of the partial pressure of the ideal gas in a mixture of ideal gases, and it is giving me the condition for equilibrium with respect to matter change. Now we are going to look at next how the chemical potential varies with respect to the composition of the system, and that would be the topic of our next lecture. Thank you.